Hello, everybody. I'd like to welcome you all to DNV Maritime's global webinar, Digital Twin Technology for Dynamic Positioning. On behalf of the presenter and myself, I'd like to thank you all for attending, and we hope that you find this webinar interesting and enlightening. My name is Simon Adams. I'm part of the regional communications team here at DNV Maritime. I'm speaking to you from Hamburg and very happy to be acting as your host today. Today, we'll be looking at a fascinating, innovative, and highly technical area of the maritime industry, dynamic positioning and the use of digital twins. DP systems are some of the most complex systems on board vessels today. They must be consistent and reliable to ensure safe and efficient operation. So over the last few years, DNV, alongside its industry partners, have been pioneering the use of digital twins, simulated models of vessels that can test systems instructions and structures under many different scenarios. Today, we'll be looking at how these new tools can be used to assess, test, and improve DP systems. We'll have a look right now at how the webinar will be run. So your microphone will be muted for the duration of the webinar, but you can ask questions at any time by typing into the chat box on the right-hand side using the orange arrow there. And we'll answer as many of those questions as we can within the time that we have today. I'd also like to highlight that the webinar is being recorded, and this recording, in addition to the slides, will be available after the webinar finishes. So let me introduce our presenter. Today we'll be hearing from Luca Pivano, Principal Specialist in DP Simulations, Control Systems, and Cybernetics Advisory. And of course, I'm your host. And now, before we get started, we'll have a quick look at the agenda. We'll be looking at the different types of digital twins and the different benefits they offer, the application of digital twins in the DP segment, especially concerning offshore wind, drilling, and offshore loading, some insights into the new DNV ST0111 and how that's been used already today, a demonstration of some of our DP capability web tools, the use of digital twins for low-speed maneuvering and tug assistance, and then there's some discussion of the OSP, the Open Simulation Platform and Simulation Trust Center, and how that's been used by one of our customers already. Then we'll have a Q&A session. So once again, I remind you, you can type in a question at any time using the little orange button there. And without any further ado, let's go into our first presentation. Luca, I hand over to you.
Thank you, Adams, Simon, for the good presentation. Good morning, everyone, and good afternoon for the one joining from Asia. So today, as Simon has introduced us, we are going to talk about the digital twin and application to dynamic positioning. There are typically many definition or different definition application of digital twins. Digital twin, you can say, is an asset. Digital twin is a virtual representation of an asset. Basically, you want to build a model of your physical system, and you can use this through the vessel lifecycle from design, early concept to the building and operation phases. And then the idea is that you maintain the digital twin along the whole vessel lifecycle. There are different ways of defining digital twins. For example, you can have analytical models for structures and hydrodynamics. When you look into fatigue, you can look into different properties of mechanical parts of the hull and the structures, things like that. You can have information models. So you can, for example, you can navigate into 3D world, and then you can click on components and get information about the different systems that are on board the vessel. You can have digital twin on sensors, process data, networks, etc. What we are focusing here is digital twin that try to predict vessel performance in terms of positioning, in terms of motion, and this is done by time domain simulations and models. So why we do this? Typically, if you can work in a digital environment early on, there is very little risk because there is no risk on damaging hardware and components. You can do a lot of changes quickly and test them and find, for example, that your vessel is not suitable for a certain operation, etc. If you sort of find out during operations And if you want to do more testing in the real vessel, this is very expensive and also is more risky, right? Because if you find something something later in this project in process can be very expensive. So, okay. Typically, when we look at dynamic positioning and sort of simulation with digital twins, we were typically looking into finding the limiting weather condition where the vessel can maintain its position and heading. Here we see an example of a shuttle tanker. Is working with the weather coming towards the bow here. On the right side here, the circle, you see the watch circle, which means shows the position of the vessel, the footprint. On the top here, you see the heading, so the ability of the vessel to maintain its direction, right? Now we are increasing the weather. We see that the vessel is still able to maintain its position in about 2 meters, but the weather is increasing, and you see the vessel is slowly losing position, and the heading also is hard to control. So eventually the vessel will lose position, and in this case we would say this operation condition, this weather is too harsh for this vessel to operate. This is one of the sort of typical application. Lately we've been moving more into workability. So for example, you see an example here. The idea here is you want to assess if you're able to send people, transfer people via motion compensated gangway from, for example, an SOV to a fixed oil platform or a wind turbine. And in these cases, we are looking into more like not only the limiting weather conditions, but for example, how many days, how many hours during the months you can transfer people from the SOV to the platform. There are different ways of running this type of analysis and workability and limiting weather conditions. The two main, let's say, families of analysis are called the static and dynamic simulations. When we have a static analysis, so basically what happens is here you get the weather forces. You see wind, current, and waves here. We increasing the wind, current, and waves, and then you basically, in the static case, you fight back with the thrusters. And then when you reach the point that, okay, I don't have any more thrust, then you stop there, right? And see that's your limit. So in the static simulation or analysis, there is no vessel motion. It's just a pure balance between the forces. So you get the environment against the thrusters. So we know that in reality there will be dynamics because the real situation is that the vessel will move, right? So we use something called dynamic allowance, so sort of a buffer to say, okay, we need to reserve some thrust for dynamics or increase the dynamic forces in the analysis just to account for those dynamics which are in reality there, but they're not really accounted for in this type of analysis, the static analysis. And another thing which is important to point out is that if you have, for example, fast thrusters, you're able to deliver the power quicker than for another case. You're not really rewarded here because there are no moving parts. There is no dynamic of thruster, dynamic of generators. So you don't gain anything when you run the static analysis if you have faster thruster, for example. While when you run dynamic simulation, the difference is that we are not looking at really at balancing forces. Well, we are mainly looking into the vessel position and try to control the vessel position into what we call the set point, is the place where you want to be, right? In this case, you see that we consider the full vessel motion, both due to the first order waves and the dynamic positioning. And what you get a bit more insight of the vessel performance, because you can also add, for example, the gangway motion, you can add the crane motions and etc. So the two main differences is that the static, the vessel doesn't move, and for dynamic analysis, you can consider the full motion of the vessel. When we run these simulations, we use typically our standard DNV ST0111, which is the standard for assessing dynamic position capability. To make a long story short, basically the standard is different levels. The two main differences, we have 3 levels for static, level 1, level 2, and level 2 site. and 2 levels for dynamics, which is called level 3 and level 3 site. The slides will be distributed. You can read the text later, but the main difference is that level 1 is a very simple method. It's mainly for monohull vessels, and is prescriptive, means that there are formulas for everything. So anyone that does a level 1 should get the same results, because it's just really punching in the data, and the formulas are the same for everyone, and the coefficients, etc. Then if you want to use your vessel specific data for the thrusters, for the wave coefficient, etc., you can use level 2. And then you can use level 2 site if you want to use a site environmental condition, because level 1 and level 2, they use a Beaufort environment scale. So it's mainly for benchmarking. While if you want to run capability for the place where you're going to operate, then you do the level 2 site, which is the one that we use the most, together with the level 3 site. If you want to look into dynamic simulations, where you look at the footprint, you look at the time series of power, how the power is distributed, etc., then you go to the level 3 and the level 3 site. Again, level 3 is mainly for benchmarking, while level 3 site is more for your site conditions, so your environmental condition in the area where you want to work. And based on experience, level 2 site and level 3 site are the analysis that we run the most. How the standard is used in industry? There are many energy companies that require the use of our standard for tenders and operational planning, among others, Total Energies, Equinor, Ørsted. It's also used in the shuttle tanker guideline in the North Sea. It's called NURG 140, where our standards is required, and also the use of the web tool that we provide with the standards. I will go back on this later, but the main idea here is that in the tool we have a share function where you can share the vessels between different actors, such that the vessel can be created, a design, a new build, and then can be transferred. So reuse of the vessel models through the vessel life cycle. So it can be transferred from the designer to the yards, to the owners, etc. So where do we use the digital twin? There are different areas where we do that. For design, for example, is a lot about right sizing these days, right? 20 years ago, we were building a lot of platforms to supply vessel in the North Sea with the giant engines. These days, it's more like finding the sweet point, balancing performance and cost. So we work a lot on thruster layout, rating, power systems, configurations, redundancy design, etc., just to find the right vessel configuration. It is used a lot on operational planning, so you can run simulation and find out what is the operational window, what is the limiting whether the vessel can operate on different configurations. And of course, contingency is also part of it, is very important. For example, if you have one generator auto maintenance, you have thruster auto maintenance if you lose part of your equipment, etc. Or we have been some cases where we did some simulation, because due to vibration, a tunnel thruster could only work up to 80% of its power, right? So there are cases like that where you have reduced power or reduced functionalities of your equipment, so you can run this and find what are the new limiting conditions for the operations. And these are used typically as input to operational guideline, like activity specific operational guideline, or for drilling well specific operating guideline. We've been using this for positioning strategy. For example, I have some example later, how optimal place the heading of your vessel towards the waves, towards the current. And sometimes we run what we call the workability, operability, where you try to estimate, for example, how many days a month you can operate in different areas. For charters, it's been used as a tool for vessel selections. One of the idea of the standard was being able to compare apples with apples. So this is also one of the sort of the benefit of using the standard, is to in the tender phase to be able to compare the vessels, and have sort of decision based on that. We did a project where a drill ship lost one engine due to malfunctioning, and then the vessel was put off charter. But then we did some simulations, and also we considered the loss of that engine plus the worst case single failure, and still the vessel was working in an area with not much weather, so the vessel was still able to maintain safely position in most of the conditions. So the vessel was hired back into operations. And this is what I meant about fair tender process, because the idea is that you're able to compare apples with apples, so it's easy for to compare different capability plots. One important factor is that that we always stress is that since we introduced the static and dynamics simulations, a static is simpler, cheaper. The dynamic is more complex. You get more insight, but it costs more. It's important to say that you need to use the right method based on what you need. So sometimes it's just okay to use the static analysis. Sometimes if you work on harsh conditions or critical situation, then you need to get more insight about your vessel performance. So the benefit of using DNV and the digital twin and the peak capability study that we perform here is different. First, we can help operators and vessel owners to choose the right vessel, and the idea, you want to have a certain uptime, right, or reduce the non-productive time. And as I mentioned before, you don't need to get the best vessel out there. You just you get the right vessel. Maybe you get not the best, but some vessel that can work and maybe is cheaper to run, because we know that overpowered vessels are very expensive. But at the same time, if you don't pick the right vessel, you pick a vessel that doesn't have enough power, enough capability, then you end up in waiting in weather, and that is also costly. We help our customer reducing time for tenders by providing comparable bids for tenders by using the standards and our tools. We can help the operators to choose the right configuration, see what is the different configuration and power configuration gives in terms of fuel consumptions and emissions to reduce operating cost. We help vessel owner to select the right vessel and to check it, if they fulfill contract requirements. And then we work a lot regarding operational planning to understand the limiting condition to reduce risk of incident and accident. And of course, we are third-party organization, so we don't have any interest in different things. So we provide our third-party judgment on this. Okay, now I will give the word to Simon for a quick poll that you will give you a possibility to express your thought about digital twin, and then we will back to Simon.
Thanks, Luca. So now we're calling on you to offer your insights into what you're thinking about the digital twin technology. So we're asking what you consider the biggest benefit of a digital twin. So if you can click on one of the options there, if it's best as a tool for right-sizing vessel design, a tool for selecting the right vessel for different operations, it's best for giving insight into vessels operating limits in terms of the weather conditions, or to support environmental sustainability. So you could click just directly there into the poll. We'll give you about a minute or so to click, and then we'll have a look at the results. And just while I've got you here, I can remind you that you can click on the question button anytime within the webinar to type in your questions. You don't have to wait for the end of the webinar. You can put those in. So we'll be pre-sorting and looking at the questions as they come in. So we've closed the poll, and let's have a quick look at the results. So here we've got really the largest proportion of people looking at the insights on the vessel operating limits in terms of the weather conditions there. And the other ones are more or less even, although the lowest is there looking at environmental sustainability. Luca, what do you make of those results? Are they backed up from what we've seen from our customers?
Yeah, I think it makes sense because eventually you want to reduce the risk in the operations. They are a little bit combined, right? Because if you select the right vessel, in a way you will reduce the risk during operations. But of course, the thing is when you run simulations beforehand, right? You can run a certain amount of cases, while if you do this during operation, you might change the condition all the time based on the actual condition. So you get a better insight on what it might come in, in an hour or in 6 hours or in the next day. When it comes to support environmental sustainability, I think in the future maybe the 7% will be higher because of the requirement that will be given for for documenting your environmental sustainability, also for dynamic position. So this will be probably higher in the future. Yeah.
Thanks, Luca. And now we're back to the presentation.
Okay, thank you. All right, let me go back to the presentation. Yes. So one of the cases is that I would like to present here is the walk to work and the application on transferring people via motion compensated gangway. The idea here is that we want to try to maximize workability, right? So we want to be able to transfer people when you have to and when you need it. The simulation that we run is for predicting if you can send people on the gangway. And the way we do it, we model the vessel, we model the gangway with gangway specific limits, and we can run simulation on different sites using also as I mentioned before, the activity specific operating guideline. In this project here on the right hand side, the idea was to replace the helicopter ride with a fast cruise vessel. So here you see one of the Damen vessels is 7011, is very fast. It's fantastic speed, so it's possible to replace helicopter ride because this is very fast. But when you look into transferring people, then you need to, of course, run simulation to see what is the limit in whether you can put people on the gangway. You see the gangway on the stern is also designed particularly for this vessel, motion compensated. So you need to consider both aspects, right? The speed aspect is good when it comes to replacing helicopters, but you need to make sure that you're able to transfer people on the platform when you need it. Another example here is in the North Sea. This is Useberg H. This is Equinor field, and also they use motion compensated gangway for transferring people. And then here as well, you want to know the North Sea is very harsh, right? You want to know when you're able to transfer people, what is the limiting weather condition, etc. And one of the takeaway from this is that the gangway here was increased. The first gangway was 26 meters, I think, and then they put a longer gangway. So that was sort of the easiest action in order to increase the workability, right? To have a longer gangway so you can accept more motion on the vessel. We've been working quite extensively in offshore wind as well. The goal is the same. You want to see when you're able to transfer people to offshore turbine for maintenance, and same as for the oil and gas application. It's important that you look at this as a sort of system, a whole system, because for example, you can see if you go to the gangway, the vendors say, oh, our gangway can work up to 4.5 meter HS, which is correct, but it depends where you put it, which vessel you put it. If you put it on a vessel which moves a lot, then it's not the gangway that will be the limiting. Is the vessel will move too much, and then in turns it will exceed the gangway limits, right? So as mentioned earlier, we look at the full vessel motion, both the dynamic motion, the dynamic position in motion, and also the motion, the first order motion in waves. You see this vessel is pitching a lot. So if you had the gangway on the stern here, you get a lot of steepness, right? So it will be too steep for the workers to walk on. It's important that you use gangway specific models and with the limits. And I think is another thing which is very important is that you should not use only the gangway mechanical limits, but you need to use the human factor limits, which are typically set by the energy companies when it comes to stiffness rate. The velocity of the telescope here also is important, because typically gangway can do a lot more speed than is allowed to do to transfer people. And you need to do analysis which are size specific, right? You need to do it for the right site where the vessel will work on. This is similar project we had for oil and gas. So this is a platform that is being built, and in order to do maintenance, they need to have the vessel available around 88-90% of the time. And if you are not able to find a vessel suitable for transferring people 90% of the time, they would have to put living quarters on the platform, and that would cost a lot of money, right? So we did simulation on this with different weather scenarios for all year, for each month, to find out, okay, are you able to get up to the 90% workability that you need to transfer people? And the answer was yes. Otherwise, would be basically a redesign of the platform and a lot of added cost. Similarly, we work with drilling applications. It's the same idea here, really. You want to predict your operations. You want to make sure that you're able to drill on different conditions. And what we do here is that we use riser forces. So you have the riser, the drilling riser, connected to the BOP, the blowout preventer here. So we also simulate the forces from the riser to the vessel. And again, what is important here is need to use site-specific weather conditions and well-specific operating guidelines, right? The operating guidelines tells you, okay, you can only use thruster up to 50%, 60%, depends on your power configurations. So typically, we never run cases where you can use all your power, because this won't be like that in reality. So the idea here is also estimating if you can work, how many days a year you can drill, or a month, etc. Also, we've been working on cases where we were estimating the fuel consumption. Typically, if you drill in harsh condition, you need all generators in, all the thruster in. But if you move from harsh condition to milder condition, then you might be able to say, okay, maybe I can switch off 2 engines, right? But then the question is, what is then your new limit? How much weather can you take with 2 engines before and not lose position in case a worst case single failure will happen? So this is very important, because when it comes to sort of fuel consumption and requirement for safety are sort of going against each other, right? Because you want to reduce the number of engines when the weather is mild, but at the same time you want to keep your robustness in case of failure comes, right? So you need to sort of run simulation and cases to balance these two aspects. We have run a lot of drilling simulations, and we have a lot of model available. Probably most of the rigs out in the world at the moment. So we run a lot of this, and one use case that we had, as I mentioned earlier, we've been working in South Africa, where you have current often coming from east, and then you have wind and waves coming from west. And if you are a drill ship, the question is, where do you put your drill ship, against the current or against the wind and waves, right? So for strong current, of course, it's more efficient to put it towards the current. But for when you have a large wind and waves, you want to reduce the motion, and then you want to get face the weather with the bow, right? And then you need to find where is the sweet point, switching between current and wind directions, right? So this is what you've done, and to find out when you should move the vessel from adding to current to adding to wind and waves. We run also a campaign for validating our digital twin in South Africa on the V-rig, on the Maersk. This is a drill ship with 6 thrusters, 6 generators. Is a Samsung 96 design, the V-class series. And basically, we sat there 5 days measuring weather, measuring conditions, and then we tried to compare what we call the footprint. So this is like if you would see the vessel from above, right, top view, and then we record the trace of the vessel, the motion. So this is one of the cases where you get a bit more than 4 meter waves and 2 knots of current coming from different directions, and you see that the footprint, they are, so the maximum excursion, they are quite good. You will never get the same footprint, right? Because the waves that are recorded at sea, you're not able to reproduce it in the simulator, but you can only reproduce the statistical data, right? So we can put the same significant wave height of 4.2 meters, but you will never get the same pattern. But what we're looking at, the maximum motion, the mean motion, and the standard deviations. This is another case. You see that this was again quite a strong current from the side, and you see in blue, you see the measurement, in red is simulations. They are not on top of each other because the simulation we started sort of at 0, but the measurement, the vessel was a bit off the set point, but you see that the pattern is quite similar. This is another case where you see the sort of the size of the cloud is similar, although it's not on top of each other because we didn't start from the same positions. Also, we run simulation with where you have mooring lines helping the thruster system to stay in position. So this is called post-moor or thruster assisted mooring. So you can also find, this is typically done when you have you drill in somehow shallow water, so below 500 meters typically, where it's convenient to have the lines help you. You can also save fuel and by using the mooring lines. When it comes to shuttle tanker, is about finding the limiting condition where you can connect and disconnect when you're doing offloading. You can test different positioning strategies, what is more efficient, what gives you your higher yard limits. And we have done simulation on different models, and we have different vessel models available for simulations. One of the interesting projects we had is what is called the well containment project, which is a project we ran with a consortium in the US, which was created after Macondo incident. The idea is that if you have a leakage in the well, you would go on top with a drill ship. On the drill ship here, with a suction cone or cope, and then the drill ship can suck the oil, right? But doesn't have storage capacity, so it can send the oil through the hose to a tanker. But the idea is that the tanker has no dynamic position capability, so that actually the tanker will be switched off and it will be connected to a hoser, so a cable here to the drill ship. So the drill ship has to withstand the weather, but also keep the tanker in position, which is also helped by a tug. So we did all the simulation to understand how much weather can you take. If the weather changed direction, how are we able to change the direction of the oil convoy, how much time it takes, and etc. And how strong should the tug be to keep all the convoy in position. So this was a very interesting project. Okay, now we'll go dive a couple of minutes into the update you're gonna have. We are working on the new update. It should coming up around November. So one of the main update is to update the standard with the use of the new and latest technology development, like permanent magnet thrusters, water jets, how to include, for example, fast response structure, etc. We will do update some of the thruster models for including the energy efficiency they have. We will add the workability guidance for the studies and different criteria that we use for probability, for example, for walk-to-work and drilling, etc. We will have a new definition of thrust utilization. So what we call effective thrust utilization, gives you a taste of how far you are from your limit. If you set the fixed weather, you want to know, okay, where I'm in my system, because I'm 30%, 50%, 70%, etc. So will be also better guidance for running time domain and dynamic simulations. And also based on the new design of SOVs, you see this vessel here has two skegs, one in the front, one in the bow. At the moment, the standard only includes the skeg on the stern, and now we will have also the possibility to have the skeg also in the bow, and we have some other stuff. So if you have question about this, you can reach me, and then I will answer you. Also, if you have input to the standard, very welcome to send it to us. We've been also working together with the IMCA work group. I've been part of the DP work group for the new DP capability plot specification, which will come up for hearing soon. I think is a lot of good work has been done there by the group. A lot of changes from the previous version, where we will have both dynamic and static analysis included, and a lot of new things regarding definition, framework, and guidance, and for reporting. So this will be soon ready for hearing after the end of June. I would like to spend a couple of minutes on the tools that we have. Most of you know that we have a web tool for running DP capability analysis for level 1, 2, and 2 site. Let me see if I able to share something with you. Give me a second, it's coming now. This one here, yeah. So this is our platform where you can have different vessels. I just want to highlight what is new, what is coming also now. As I mentioned earlier, the platform will allow you to share vessels. So you can share vessel among your team, amongst also your partner, your customer, etc. You can lock the vessel such that you could share it only read only. But the main point is that you have only one vessel, one source of data. So if you work in a company with multiple people working on a fleet, then it's the same fleet for everyone. So there is no version lying around. We are coming up with a better calculation system, so where you can run multiple runs at the same time. So you don't need to run one at a time, but you will be able to select the runs you want to do and run it, and then come back when it's ready. Also, we will improve the reporting functionality and the tool for comparing different vessels. So we will have a soon a version coming up, a new release, and then we are constantly working on making new improvement. For example, what we did, we added the we added the run for the NUROG, where you get all the data fixed from based on the NURO guideline, so you don't need to punch in what is sort of provided by or required by the guidelines. The IMCA also will be here when the new IMCA standard will be out, and you can also today you can show the plot on different formats based on your wish and so on. So at the moment we have about 3,000 users. They're growing and we get good feedback. So if you have any feedback, any improvement or input to improvements and everything, please send us your inputs. Also, we have a level 3 tool, which is quite similar to the one I show you now. So we have a web app as well there, where you can control your simulations, and you get the results in of course from the time domain instead of getting the result from the static analysis. You can do the same. You can do reporting. The only thing is, in this web app, we are making the models are more complex for the moment. DMV makes the models, and then we make the models available for the customer. They can run simulation and with different conditions and get reporting as well. Okay, I will jump into the last part of the presentation, which is about low-speed maneuvering applications. We did some project where basically we want to estimate if you have a vessel coming into port, how many tugs are needed for getting into position, getting into port, how many tugs, the size of the tugs, the speed that will be the vessel will be moving in, and what is the limiting condition for example for an existing series of tugs, and how the tug configuration could work for getting the vessel into position. This is a project we had in Greece, where there is a regasification unit. So due to the shortage of gas in Europe, there are more LNG carriers coming into the ports, right? And this is basically a regasification unit that gets an LNG on the side here, and then they uploaded the gas, and then they will process it and send into the network. So, and the idea here was that, okay, how many tugs do we need first for getting the LNG into the close by the FSRU, and then if the weather is picking up, how many tugs do we need to move for moving the FSRU from the jetty into the port to be safe. So this is also something we can do, and it's similar to what we can do for cruise ship, where we estimate if you can get into ports, if you can do maneuvering around the ports, different conditions, and especially you could run simulation on new ports where new ports are not even built, right? To see what will be the sort of the performance of the cruise ship coming into the port, the new port. So to conclude about the work we've been also doing with the OSP, the Open Simulation Platform, and the STC, which is the Simulation Trust Center. The Simulation Trust Center is sort of, we can call it an interface or a platform to put on top of the Open Simulation Platform, which is an open source co-simulation platform. The idea here is that you want to be able to co-simulate, which means simulation coming from different vendors. For example, you have a trusted vendor which create a model and make the model available to the platform. You have maybe an engine manufacturer which makes his own model. And the important things about the STC, the Simulation Trust Center, is that they ensure that the IPR, the sort of everything behind the model is not shared between different actors, right? Because the vendor A doesn't want to show what's inside the model. So the model is shown as a black box, but is available for simulating. And you don't need to also to move people on different models on different parts of the world, right? You can simulate online in the cloud, where people can connect their models, and then you can run simulation where sort of all organized or synchronized by the STC on top, and then you can run different steps and find the sort of the vessel performance on different conditions. And this is what we are doing with the project with the Damen for the CSOV 1920. So we are using, or they're using the STC to simulate, create a digital twin and simulate this vessel here in different conditions. And the idea again is to see if you're able to transfer people via the motion compensated gangway. And here different partners and different vendors are delivering different models, right? We've been tasked to deliver the hydrodynamics model, but the other part of the model comes from the actual vendors. So you can connect everything in the as shown here, right? In the STC, and then you can run simulations, and then you can run performance on different weather conditions and see if the vessel is able to perform as intended. So that's it from our side. You will get the slides available, also the registration of the webinar available, but also you feel free to contact us if you have any questions, any doubts, anything regarding what has been presented. All right, then we open up for the Q&A section. And then I give the word back to Simon.
Thanks, Luca. As you said, we have a number of different pages there that people can check out. if they want to delve a little bit deeper into the subject once we've after the webinar. But right now we have questions from our audience. We have a whole bunch here. Thank you so much for sending those in. You can keep doing that as well. Just click on the old orange button there and pop those in. Let's start off. We have a lot of detailed questions from everybody with a little bit around the data that goes into a digital twin. We've got some questions there on what kinds of input data are necessary for the simulation. What does a 3D scan data help to create the model? And for specifically in drilling, do we need full meta-ocean data, wave current patterns and things like that? So we've got quite a few questions about the types of data and specific data that's used in the models.
Okay, thanks for the data. So the type of data is of course depending on the application, right? When it comes to drilling, and now we are looking at motion limitations, motion in waves, current and wind. So obviously you need sort of the hydrodynamics properties of the vessel. So load condition, we use the 3D model of the hull to calculate the wave forces and the wave coefficients. We use wind coefficient and current coefficient, which typically comes from either CFD or they come from model test to build up the forces. We need to know the dynamics of the equipment that is used for dynamic positioning, but in this case it's enough with the generators. So the power rate with the thruster, how fast they move, they rotate, for example, how fast the propeller will go from 0 to 100%. We use the in the case of the drilling, we use also the riser stack. So which elements are in the stack and their diameter and their resistance, the coefficient resistance for each section here to calculate the forces. So when it comes to 3D model, back on the question, is the only 3D model that we need is from the hull to calculate the wave forces. And then of course we need the environmental conditions on the area. Can be done in different things in different ways. If you get statistics saying that okay, 80% of the time you get waves up to 4 meters, etc., you could use that and run different scenarios on different fixed weather. Or sometimes we even get 30 years of weather, like we had in the project for the SOV, where you get 30 years of weather every hour, and then you can run the full actual weather and then check the operability based on the weather that has been registered in 30 years or 10 years in the location. Yeah.
We had a sort of an update there, an extra one that came in on how often we would need to update the digital twin. I guess this is also related to the data that we've got.
Yeah, that's good. So this is a very good point, because you start with a model based on physical properties. The vessel is not even built sometimes, right? So you start with the length, the breadth, and the load condition, the weight, and all these properties, thruster sizes, thruster power, etc. And then you build your first version of the digital twin. And then after it's built, you need to might refine it, or we call it calibrate it. If you get, for example, even before it's built, you might get model test data. So you do the first calibration there, where you get model test data, and you can input this into your digital twin. And then when it's put in operation, you should be able to compare the actual output of the digital twin with the actual output from the real vessel. One of the challenges there is that not all the sites and all the vessels, you're able to measure wind current waves with the right sort of definition and the right precision that you need. Because what's the most important is that if you have garbage into your model, you get garbage out, right? Sorry for the expression, which means that you need to measure the weather and measure the vessel performance. Measuring the vessel performance is quite easy. There are sensors, there is everything available, but you need to be able to measure the weather conditions properly, such that you're able to calibrate. How often? This is something we are working on. I don't think there is an easy answer there. In some places, there is more seasonality, for example, which means that you build a model, it works fine for 3 months, and then you see maybe it comes to the winter condition, then you get a bit more discrepancy between motion and things like that. So you might need to recalibrate it. But some other places there is less seasonal variations, so you might be able to do less frequent updates on your model.
Yeah, so continuing on the sort of data theme, but taking it to the next step, how accurate have the digital twins proved in practice? Do we have sort of good numbers around how they're matching up to actually real world performance once we're able to get that data in?
We did some full scale trials for let's say calibrate and to compare the performance of the digital twin with the actual data. One is the one I shown here on the Maersk Venturer on the V class, which we got a good agreement. I have to say that here in South Africa, they measure the current with a velocimeter Doppler. They measure the waves, so we got the full stack of measurement. We did also some full-scale validation on a platform supply vessel in the North Sea, where we get a bit less precise weather data, but we were looking sort of the footprint and basically get feedback from the DPO. Okay, what feeling about how far from their limits are, and compare this what the plot was saying, and that was also quite good in agreement. So we are working now in a project where we are going to do this for SOVs, for transferring people via the gangway. So it's yeah. So we've done some work there, and I said you can start with the first version of digital twin, but then it's important that you're able to calibrate it with the actual data.
Thanks, Luca. Let's we've got a couple of quite specific questions here that we can maybe knock off. Is the L3 app now a commercial product that a customer can use or buy?
Yes. It is commercial. As I mentioned here, we are building the models for the customers. So it's not like a self-service where you can punch in the length and put this your coefficient. We do that because the models are more complex. But we can make a model available for any customer. They can run their own simulations. Yeah.
Let's see if we've got a couple on the walk to work.
Maybe I can read one because there is a question regarding the gangway and which limit are applied.
Yes.
Which is I don't have a slide on this, unfortunately, but there are different, as I mentioned, there are two different type of limits. One is the mechanical limits, and the other is the sort of human factor limits. So the mechanical limits, for example, if you have a gangway, they can go plus minus 5 meters in displacement. Displacement is, let me go back to here. This is okay also. Displacement is of the telescope is the maximum sort of excursion the telescope can have. Let's say plus minus 5 meters. That's mechanical, but in practice, for transferring people, you might go up to 3.8 meters, not all the 5, right? So that's one limit. The speed as well. The speed of the telescope is another limit. It's very important. Typically, is around 1.2 meter per second, somewhere around there, 1.2, 1.3. But the gangway, they typically can do 3 meters per second, but you can't mechanically, right? But you don't put people when they do 3 meters per second. So you need to add those limits. Same with the steepness, right? The steepness is what a worker will feel, the steepness a worker will feel when walking to the gangway. some places you can use 10 degrees because of regulation. Australia, for example, even your gangway angle can reach 20 degrees. You will never be able to use that because the regulation says, okay, 10 is the maximum. Some other places is 12 degrees, some other places is 14 degrees. And those are also factors due to regulation which are here. And then there are the steepness velocity. So the rate of the steepness will change also. 3 degrees per second, for example, although the gangway maybe can do 6 degrees per second, right? So, but you need to use the human factor in there. Accelerations also are factor. Vertical acceleration, horizontal accelerations are also used in those analyses. So these are the typical limit that we use.
Another couple of specific questions there. Whether the simulation can take roll reduction equipment into consideration.
Sorry, Adam, can you say it one more time?
Whether the simulation can take roll reduction.
Oh yeah. This is very important when you run this type of simulation. So we modeled the effect on the roll reduction tanks, for example, or devices in the roll motion rows. And this can be done in two ways. Either there are software that can help us to tell how the resonance will move and how the peak of the resonance will be shaped, or there are also, we've been using in some cases model test to calibrate the digital twin performance for the roll part. Yes, it's very important to use them. Yep.
And the main differences between the DNV and IMCA guidelines for DP.
Oh, this is a spoiler because the IMCA is not yet released, but it's let's say the DNV was the first sort of standard that included also the dynamic part, right? Now IMCA also is including that, and IMCA is sort of looking into more like as minimum you should have this effect, for example, thrust losses, this loss, this coefficient, all this sort of particularity in the methodology. And then for each of these elements, the IMCA will look into, okay, you can use either DNV standard for this, you can use the ABS standards, you can use IPA, you can use the old IMCA. We baked into there. So it's more like setting requirements on what you should dam your simulation and how you actually do it. You can read from different standards, because the goal of IMCA is not to write a new sort of Bible or standard with calculations and methodology, but to write a framework around on how to run analysis and where you can find the sources for including the different effects that are required.
Thanks, Luca. So maybe to wrap up, we had a few questions around the future of the tool, how we're working to improve simulations with the twin, if we're using any machine learning systems, and how we expect this digital twins to develop in the future, especially as it relates to the DP capability.
That's a very good question. I think we already did some work in DNV, including artificial intelligence, machine learning into model prediction. One way of doing this, you start with your physical model, right, based on your vessel characteristics, and then you get sort of performance, and then you get the actual performance, and you could model the gap between what your physical model and the actual model does with artificial intelligence. So you might not need to model the whole process. You might model only part of it, and of course when you build your vessel you don't have any data, so you're not able to use artificial intelligence from day one, but you can sort of add blocks later when you get more information. So for me I'm thinking that the artificial intelligence can help on the calibration sort of activity of the simulator. It's a lot of parameters, right? This is something we are working on now. Say, okay, you have hundreds of parameters. Which one are you going to tune to match the performance? This is a really high, it's an optimization, process. And I think artificial intelligence can help into that if you train it correctly.
Thanks so much. Everybody, we've now arrived at the end of today's webinar. I'd like to thank Luca for this, his insights and on this really interesting and fascinating topic. And I'm sure that the presentation has helped our attendees deepen their understanding. As we said before, the webinar has been recorded, and we'll be emailing you a link so that you can get the webinar as well as the slides in the next few days. As well, there are many webinars on the DNV website that you can check out, both with the recordings and slides. You can get those all for free. Download them, have a look. And as well, we had the slides before showing where you can investigate more about the both the digital twin and the DP capability services from DNV. Thank you so much for attending. Take care, and we look forward to seeing you all at our next webinar. Thanks so much, Luca, and goodbye, everybody.
Thank you, everyone. Bye.